Hello, everyone. This is the new edition, the new session for the International Interactive Technical Talk. And this time, a very important topic, especially for the youth, young engineers and non-engineers who are looking forward and pushing us as engineers to think about Mother Earth, sustainability and geotechnical engineering. Today, we have with us three very dedicated, enthusiastic, and renowned engineers, starting with Professor Mohammed Mizanur Rahman, who is in Australia, Dr. Sara Rios, who is in Portugal, and Tone Ratcliffe Smaavik, who is in Norway. So we're bringing together from all around the globe specialists to tell us about sustainability. I like to give the floor to Professor Mizanur Rahman. Please, if you like to share your screen and start this session. Thank you all for joining. Feel free to tell us more about you if you want.
That's okay.
Wonderful. It's interactive, so if you have something to to tell Mizanur, you can interrupt me.
Thank you, Mark. Thank you for giving me opportunity to talk a little bit about TC307 sustainability in geotechnical engineering. What I'll do, I'll give you a little bit overview of the TC, and then I'll talk a little bit about the perception of sustainability. And then I'll talk a little about my research when we apply to evaluate sustainability in different applications, then what are the challenges we face. The TC307 has terms of reference. It includes 4 different objectives. The first one is the dissemination of the concept sustainability. That's rely on 3 pillars. In some definition, it could be more than that, but in general, it's 3 pillars. So it has to be cost effective, environment friendly, and socially acceptable. The area it's overlap over here is the most sustainable practice. Often it's very difficult to achieve. Now, within the TC, we try to develop guideline and recommendation in some priority areas. So we had 4 of those, 8 of those. First is innovation application of sustainability in geotechnical practice. For example, if someone designing foundation in common geotechnical practice, and whether they can be used innovative ideas to bring sustainability. Very common one is use of material or waste material. I will talk about a little bit of my research on that. Then there would be some concept of using and reusing ground space. For example, ground space used for energy storage or carbon dioxide storage that also brings sustainability in our practice. The other priority areas is like renewable energies, geothermal and mining. Geothermal, I know that there is another TC on energy, but this also brings sustainability in our practice. Sustainability indicators is a big debate. Whether a technology is sustainable or not, it depends on all these, at least these 3 pillars. Often something cost effective in a country, it would not be effective in other country. It's socially acceptable in Australia, may not be in the United States or Europe. It is environment friendly in some places may not be. It might be very costly for environments. The 6th priority area is socioeconomic impact and geoactivity. Some geoactivities could affect the socioeconomic significantly. For example, some developed countries export waste material to other countries, and that is stopped. So it impacts socioeconomic. Also, geohazard and mitigation is part of that, and geoethics and geodiversity. We want a diverse practice that also brings sustainability in our profession. We also look after or try to get involved and assist conferences In general, this TC involved 3 to 5 conferences per year. Sometimes it's more, but during the COVID, it reduced. The one significant involvement we had for international conference for soil mechanics and geotechnical engineering in Sydney, we had 2 sessions, one face-to-face and other ones online, and was enormously popular. We also involved in future events, for example, CREST in Japan in 2023, then European Onset Conference in Portugal, Transportation Geomechanics Conference in Sydney, and also there is some activities in line with Geo Institute AAC. We also try to involve with industry partners. That I haven't included over here. So this is what we do as part of TC307. Now, what I will do, I'll show my research based on case studies and challenges when we try to measure sustainability of the project. So what I have over here are 2 pavement construction methods. One is with interlocking block pavements. So on the top surface, we have these concrete blocks. They're lying on coarse sand. Then underneath, we have base course, sub-base course, and subgrade. The same pavement can be constructed with asphalt, multiple layer of asphalts. Then we have base course, sub-base course, and subgrade. What I'm looking at over here, if this pavement is constructed with reused construction and demolition material, then whether we could achieve sustainability or not. So the idea is the material over here, base course or sub-base course, if we replace with recycled material, then what we achieve in terms of carbon emission and costing. I also have a little bit of a study. If you replace this material with some environment-friendly material, then what happens? So let's go ahead. Now, over here, I have a flowchart of measuring sustainability index, particularly those 3 pillars. One is environmental benefit and the economic benefit. So for example, if we are constructing a pavement with using virgin quarry material, so when we quarry this material that needs energy and produce carbon dioxide as well, then we transported this material to the processing plant. Transportation has some cost, processing has some cost, then this material goes to transported to road construction for road base and sub base. So if we follow this flow chart, then we can estimate what would be the carbon emission, energy required, and the cost for the project. So this is standard or normalized for a virgin material. But if we want to evaluate whether we achieve sustainability with reused material, particularly construction and demolition material, usually these material transported to landfill. So there would be some energy and carbon emission for transportation. And when it goes to landfill, that also produce energy and carbon emission, and as well as operation cost and government levy cost. When we divert this material on this line to this green line, then we have likely chance to achieve sustainability. Let's see what happens. So we transport this material to a processing plant, so it has an energy and carbon cost, then the processing cost, then we transport them for the sub-base and base construction. If we do that, then we can look at environmental impact, the cost associated with, and also we can look at the social acceptability. So let's see what happens.
Such an interesting slide. I took a snapshot.
Oh, that's great. I'll be sharing with you anyway.
You have a copyright on this?
No. Only thing I would say, it's a very interesting slide, and I have a paper on it. Quite thorough and details. Understand
the information. I hope it's pretty accurate.
Yes.
So I want to ask you here about mixed construction and demolition waste. You make the bricks out of reused, demolished.
We are looking for granular material for base and sub-base. We are not making brick anymore. We're just using the granular material for base and
because I heard of those bricks they make from construction waste.
Yes, I'll talk a little bit again.
I have a name and a patent. I forgot the name, but
yes, that's correct. That's correct. And really interesting observation on that too. Now, I think you're interested on the metrics over there. For example, over here, the energy from the quarry and carbon emission, these come from a particular reference. Now, if you look at literature, there will be a range of reference, very confusing, ranging from $5 to $500. But when someone is using these metrics to calculate sustainability, they need to look at the local technology, local material, local cost. As I said, sustainability would be very subjective. So something sustainable in Australia may not be sustainable in Europe. So people need to understand the context over here.
Yes, the three
Now,
circles are in
yes,
playing
yes.
together.
Now over here, what I'm looking at, the benefit. So social benefit, if you are constructing the pavement, there would be, the appearance would be exactly same if we use recycled material or virgin material. So we assume in this case, the social index remains same. But what happened, the environmental benefit in terms of carbon emission and the cost, the benefit increases. And that increase will depend on the quality of subgrade material we achieve through the recycled material. So one of the indicator would be elastic modulus or a resilient modulus. So pavement design is still elastic design. So we heavily depend on elastic modulus. Now over here, if we look at the benefit cost ratio, economic and environment, and then if we look at different elastic modulus, if we increase elastic modulus, as you see over here, benefit increases, exactly same over here, benefit increases. So we can clearly see how much benefit we're gonna get during using recycled material. That depends on how much improvement we could achieve. So virgin recycled material may not achieve that kind of improvement. It might be somewhere over here. If we want to achieve that improvement, so we need to use some material so improve its property. It could be cement or something else. So I'll talk in my second slide about that. Now over here, if you see the metrics, I said very simple way to define sustainability in 3 pillars. Some people could come up with multiple pillars. Now, for example, over here, I still have the social acceptance, environment, and economic. For this project, we look at risk. If we design this pavement exactly same way, using recycled material or virgin material, the risk would remain same. But it unnecessarily one more index we're getting in to our sustainability calculation. So we need to be careful, like unnecessarily whether we are making it more complex. Now, as I said, if we try to improve this material property, so what we could do, we could do some cementation of the base course material. Now, what we realize, biocementation in Australia is getting popular, and there is some big, large government projects supported for base course material improvement. So I have some research on sand. It's not only base course. These slides based on sand. So what we have done, we can use some bacteria, particularly Sporocarcina pastorale. They produce some kind of enzyme around their cell, and that enzyme accelerates urea hydrolysis, and that precipitate calcium carbonate. So if you see the sand particle over here, after the treatment, the precipitate calcium carbonate bond bridge between them and cement the particle. The sand becomes this kind of material. So this is one way using bacteria that we call MICP, microbial induced calcite precipitation. The other way would be we're looking for enzymes, and that could be extracted from plants. So in my research, what I did, I tried to find the enzyme from waste material, for example, weed. This is called paddy melon. It's grow middle of Australia. In Australia, big country, so it grows a lot. And we realized this paddy melon has about 10% biomass seeds, and these seeds are very rich with active enzymes. So if we get the enzyme, do the same process, then we can get cemented material. So these are the sand, but using plant-based enzyme. And this is cemented sand using bacteria. It's called microbial-induced calcite precipitation, and it's enzyme-induced calcite precipitation. Now, this technology could be transferred directly to base course treatment. If we do that, then what happens? So I did a little calculation on sustainability. So over here, we look at a case study, a 7-meter width road, 1 kilometer long, designed for 6 million traffic loading. And we're looking for treating the pavers, as you mentioned, Mark. Paver could be made from recycled material and also bind them with cements. So we are looking at cement-treated pavers and a subbase. For this heavy traffic loading, the subbase thickness is quite high. It's about 0.5 meter. If we look at these index again, we put risk over here, economic over here, and environmental cost, that is carbon emission mostly. If we use cement directly, in this case, the emission is quite low than MICP. Okay, it looks quite big number. Again, over here, if we look at the cost in terms of Australian dollar, cement is quite low than MICP, biocementation. So when we talk about biocementation, people think like it's sustainable, environment friendly, less carbon emission. Not necessarily all the time. Now, we have limitation in this calculation. We use a laboratory grade ingredient for our biocementation, so the cost is really high. But for industrial practice, we do not need that grade material. We could use like low grade material and could be a lot cheaper. But anyway, what do we see in this calculation? If we try to treat subbase and paver in both cases, it's not necessarily sustainable. Can we make it sustainable using the same technique? So what we did over here, a little analysis. In the next slide, instead of treating subbase and paver together, as I said, for 6 million traffic loading, subbase thickness was quite high, about 0.5 meter. If we forget about the subbase, we only treat the pavers, then what happened? MICP become the cheaper in terms of carbon emission and the cost. So the same technology, if we want to treat everything possible within a system, it might not be sustainable. But if we use it in an intelligent way, we could achieve sustainability quite easily. What do we see over here? When we are treating paper only, the carbon emission is much lower than cement. Cost much lower, not much, little bit lower than cements. So it is going towards sustainable, even though we are estimating the calculation based on laboratory material.
Fully sustainable is where the green matches the blue.
The blue is, if we do the same construction using conventional cement, and actually cement produce about 0.9 kilogram of carbon to produce 1 kilogram of cement. So we
so
have.
You want the green to be smaller.
Yes, green to be is better. This is not its absolute value what it produces. The first graph I showed you is benefit. This one is absolute value. So bigger number is not good over here. So what I think in conclusion,
why do you say treating the pavers is more sustainable than treating the subbase and the pavers? And have you tried treating the subbase without the pavers instead of treating the pavers with?
Yes, in that paper we did a different
That's
scenario.
by intuition, I would have thought you want to treat the subbase.
Yes.
As a practitioner, but intuition isn't always right. Actually, it's most of the time wrong.
No, you're right, but this is a particular application of interlocking block paper. It's not asphalt paper. The top layer is block. So you could achieve this block different way using cement or using MICP. So we thought like if we use MICP, then what happens? So what we see, it's better. It could be sustainable, but this is a new technology. We do not know about durability of this material. whether it will
Yes.
usually pavements are designed for 20 years. Yes, please.
So you said the results are coming from a 7 meter by 1 kilometer
Yes.
testing the road strip.
Yes.
Yes, I am worried, not worried, but I'm thinking you reminded me of the launching of plastics and nylon. When they launched it, they were saving the planet because we want to stop cutting trees. And
Yes.
look where we are at now. It's the biggest problem,
Yes.
plastics. So I hope the sample of 1 kilometer is not representative of millions of kilometers of roadways. So I'm not playing the devil's advocate, but we have to keep this in mind, long-term effects.
Yes, Marc, you're completely right. When it comes to sustainability, as I said, sustainability also depends on geographic location, social culture, and time. Something sustainable in some scale may not be sustainable in a bigger scale. Now, this is one example. If we just remove one part of the pavement construction, it looks better. But if we think of like same technology would use for whole sort of thing like subways and the paper, it's not.
Right.
So it's a very fluid thing. People have to keep that thing in mind.
Very interesting research. I've heard about MICP and I think it has a future. It's still at its early stages.
Yes, we are this calculation based on high quality laboratory grade ingredients, so it's very expensive.
A lot of research being done in the US also about that.
Yes.
Keep going, move a little bit faster so that
Thank you. I think this is my last slide, so I'm done. And my colleague, Dr. Sara, will be presenting her presentation now.
Thanks.
Thank
yes.
you.
Thank you.
Let me stop it.
I suppose you are now seeing my slides.
Yes.
So thank you very much for the opportunity to show what we are doing at the University of Porto on the use of industrial waste in geotechnical engineering. So most of our ground improvement solutions rely on Portland cement, and as Mizanur has just said, it has a high carbon footprint. So we need to develop more sustainable binders. And the one that I'm studying here is the use of alkali activated binders generated from industrial wastes. So these binders, they are a mixture of a precursor with an activator, so a high pH solution, and these can be from different materials. But if we use industrial wastes for the precursor and for the activator, we can significantly reduce the carbon footprint. So that's what we need to pursue. So I've tried to summarize here the advantages and limitations that we have found on these binders. For example, we tested these binders with contaminated soils and with saline environment, very harsh conditions. And we found out that, for example, a saline environment that can be not so good for a Portland cement is in fact beneficial for an alkali activated binder, because the saline water generally has high pH than a distilled water, for example. So that can be a good option. And also we generally monitor the strength and stiffness evolution of these binders with ultrasonic transducers, and I'm showing here in this photograph. And we know that soil cement mixtures based on Portland cement, they generally increase up to a certain point on 28 days, and then they remain constant. But these binders, these alkali activated binders, generally the low calcium ones, they tend to increase the stiffness and strength further beyond the 28 days. So this can be an interesting property of these materials. And also, we have tested them with different temperatures. So if we want to apply in geotechnical engineering problems, we need to use it at room temperature or air temperature. But this difference between climates, different climates and different seasons has a significant influence. So for example, if we test them at 18 degrees or at 40 degrees, that changes a lot the stiffness and strength that we obtain with these materials. So they are more suitable for hot climates, I would say. But of course, if we use it in submerged conditions, for example, deep soil mixing columns in a coastal environment, that in that case, we will require a high concentration of activator. So what we realize is that these binders, they still need an optimization regarding the type of precursor, the type of activator, and the type of soil that we are using. It's not the same recipe as using Portland cement, because that is always the same in all parts of the world, and we have a very large experience on that. So these binders, they need to be specific depending on the materials that we are using. But I think that's the aim of sustainability, to use local materials, and that has challenges, of course. So also we tried to see how to apply these binders in practice. And we realized that the same procedures and the same equipment can be used, the same equipment that we use for Portland cement materials, sub-base materials. So from that point of view, it's not an issue to apply these binders in practical problems. Also, with this project with the Universidad Militar Nueva Granada in Bogotá, Colombia, we've tested this material in a subbase, tested with this wheel test. So it's basically a wheel that goes back and forward over the layer that we are studying, and we can measure the deformations and the weathering that this layer suffers due to the cyclic loading imposed by the traffic.
Quick question.
Yeah, please.
Do you know if the wheels are going and coming with the same pressure, or they're going lifted, coming back down? And just curiosity.
Yeah, I think in this equipment, it was really at the beginning when we did this project. I believe now they have more experience with that, but at that moment, the pressure was the same, the load was the same back and forward. Yeah, but I believe they may eventually change that.
I would lift it to simulate traffic in one direction. It makes a big difference.
Probably,
Sara,
yes. Yes.
Sara, what was the tire pressure?
Sorry?
What was the air pressure in the tire?
I'm not, I don't know that by heart at the moment. Yeah. This was a project some 2 or 3 years ago. I don't remember. Yeah, that specification. Sorry.
I like this test.
Yeah, it's really an important feature that they have in Bogotá, Colombia, Universidad Militar Nueva Granada. So we like to do connections worldwide, and it was really interesting to do this project with them. So basically, one of these persons that is not really shown here has done the PhD in Portugal. So we established good relationships with him. It's Professor Javier Camacho Tauta. And that's why we had the opportunity to do this project with them. It was really interesting. Okay, so I will continue. So at the moment, we are trying to use these binders for the stabilization of mine tailings.
Sorry, Sara.
Yeah?
Sorry, Sara, I lost you because I lost my Wi-Fi. I asked, where was this test done, if you go one previous slide?
Okay, so I'll repeat that, no problem. So this was done in Bogotá, Colombia, Universidad Militar Nueva Granada. Yes, with Professor Javier Camacho Tauta, that has done the PhD in Portugal, and that's why we established this connection with them.
Wonderful, wonderful. Keep
Yeah.
going. Thank you.
Okay, no problem. So as I was saying, we are now studying these binders for the stabilization of mine tailings. As you know, this is a very big problem due to the recent accidents that occurred in Brazil. So one possible alternative is to build embankments like this one of filtered tailings. So instead of disposing the slurry of tailings in tailing dams, which is generally the most common option, we can reduce the water content of the tailing and build embankments like this one. But of course, these embankments, they are massive. They are very, very large and high in height. So we need to stabilize them. And one alternative that we are studying is the possibility to do a cemented berm to stabilize the embankment. And also we have another project ongoing to do some centrifuge tests in Delft, Netherlands, where we can do some centrifuge tests and also some numerical analysis to evaluate the hydromechanical behavior of these embankments. So what happens when there is a heavy rain and so a percolation is established on this embankment? It eventually can trigger an endrain failure, trigger some liquefaction phenomena or so. You know that sometimes this material is not so compacted as we wished, so they can still be contracted and it can suffer large deformations due to liquefaction. So this is
Interesting.
Yeah.
You know, we had the first IITT was on mine tailing with Professor Kudmani. I don't know if you watched it, but
yes, I'm following.
this
Yes,
is a new addition. We complement each other.
exactly. Yes, and I'm also working
This
with
is a
the
proof
professor.
that
Yeah, I'm also working with Professor Antonio Viana da Fonseca, which is really interested in that TC and on mine tailing issues. So that's
I have one
big
question.
problem. Yes.
To clarify to the audience, when you say alkali activated binders, what is the main original source? Is it crushed concrete from buildings? Is it recycled asphalt?
No.
From landfills?
Yeah, so we are mixing a precursor. It can be a slag, for example, or fly ash if we want to use industrial wastes, and I'm mixing that with an alkaline activator. It can be, for example, sodium hydroxide or sodium aluminate, which is also an industrial waste. So this creates a gel that hardens with time. And
so where do you go to get the precursor?
I can go to a steel industry that has slags, for example, iron slags or steel slags, or I can use fly ash, for example, from the carbon thermoelectric power plants that use carbon, for example. That's a possibility, but there are different kinds of fly ashes that we can use as well.
Okay, so the industrial waste is specific.
Yeah, yeah, we need to optimize
okay.
Exactly. Yeah, we need to optimize the binder depending on the source materials that we are using. Yeah, so that depends on the materials. So we can do alkali activated binders with a lot of materials, but of course they will not have the same properties everywhere with all the materials. So depending on the material that we use, we will need to adjust the alkaline activator concentration, the amount of fly ash or the amount of slag, and we need to optimize the binder for that specific purpose. Yes.
Same question I asked for Mizanur. Do you think we have enough in terms of amounts for saving large constructions? And
yeah, that's
create another problem by
Yeah, I know that's an important question. I believe that these binders, they can be complementary to Portland cement and not completely replace it. Also because there are other binders being studied. For example, the MIC, the microbial induced precipitation that Mizanur has just spoken. So there are a lot of binders sustainable binders that are being studied. So I don't think that one of them can replace Portland cement in all applications. I think we can choose the best binder for that specific place and the specific materials that we have at hand in that place. So, for example,
so we're still in the research process.
Unfortunately, yes, but there are some practical applications that are going on that are very promising. But for example, on the fly ash, yes.
No, I wanted to say that this explains why the three specialists are young.
Sara, I have a question for you.
Yeah.
What would be the percentage of fly ash for your project you're using in?
Yes, I'm studying that up to 30%, for example. I think that's a reasonable amount, but we can use more or less depending on the conditions. Yes, 20 or 30% of the soil, for example. A ratio of fly ash soil of 0.2, 0.3.
Okay.
But of course, there are some fly ashes that are more reactive than others. For example, if you use the ground granulated blast furnace slags, they are much more reactive than using, for example, the ladle slag that I have, I'll show you in a few slides. So depending on the slag, that some slags are more reactive than the others, and that makes a significant difference. Yes. And also the fly ash, sometimes the production of the fly ash is completely absorbed by the cement industry that also uses these industrial wastes. And in some other cases, there is a significant accumulation of these industrial waste because the cement industry cannot absorb that. So depending on the place and time, some wastes can be available or others. So we need to search for that and optimize for a specific condition.
Wonderful. Keep going. You
Okay,
see my questions ruin the time schedule.
No problem, no problem. That they are very useful.
Right.
Yeah, I just have a last slide just to show that we can also use the slags for transport platforms without the alkaline activation. So in Portugal, our steel industry produces two different types of slags. One of them is inert steel slag aggregate for construction, which has already been certified to this purpose. And this is the black one that we see here. It's very coarse. And then we have another ladle slag that can be used for alkaline activation. Yes, it's a possibility, but it's not so reactive. But also it can be used in this case, mixing with the steel aggregate here. So if we mix both of them, we create specimens that we see in this picture. So this aggregate has lack of fines, while the ladle slag is a fine powder and it has cementing properties. So mixing them both creates a cemented mixture and with very interesting results that we are now characterizing in the laboratory in cyclic conditions.
You mix it with some water or what?
Yes, to the optimum Proctor moisture content, yes.
To optimum moisture, and you compress it and wait, or?
Yeah, just compact it to the optimum point of the Proctor compaction curve. Yes, as we do in a platform, in a transport platform.
And they gain this cohesion,
exactly.
This cementation.
Exactly.
Interesting.
Another possibility is to use this slag aggregate with rubber. Rubber from end-of-life tires is also an industrial waste that can have different applications. For example, now it's very used in playgrounds, but there are a great number of applications. And one possibility is when joining with other materials, we can reduce the resilient models and increase damping. We can be beneficial for vibration mitigation, for example. So rubber has that advantage.
You
So
know, it has been.
I have a question with the binder.
Yes.
Did you have a big problem with the shrinkage or cracking?
No, at the moment, you mean this one, this mixture here?
This one, yeah.
Yeah, we haven't found any problem in terms of that volumetric instability. No cracking, no swelling, nothing of that. That was a concern that we had. We also did a wetting and drying cycles to evaluate if the temperature was creating any weathering problems. But at the moment, these didn't show. Also with hot temperatures as well, and they didn't show any instability.
That's really good, because if we directly use cement, then cracking is a problem.
Yeah, well, of course, cemented materials are always brittle, so they can have they can have some cracking due to a large number of cycles. So that's why when we test these materials, we try to use cyclic triaxial tests up to 1 million cycles to evaluate what happens. Okay, this is a ongoing process. I don't have the results of that long-term cycles, but they don't show, because as they cement with time, any cracks that may appear, they tend to be compensated by the cement that is hardening. So at the moment, we haven't seen any degradation of the material with a high number of cycles, but of course we are studying that still. So any other question? So this was basically my last slide. So thank you very much for this opportunity. And I will give my floor to the next speaker.
Dawn, the floor is yours.
So yeah, like the others, thank you for the opportunity to talk about our work on sustainability in geotechnical engineering. I wanted to take this opportunity to talk about 2 examples of work that my colleagues at the Norwegian Geotechnical Institute have been working on recently. So this is current and also still ongoing work, so that I'll show you what we're working on at the moment. Firstly, we are part of a corporate research centre called Earth Rescue, which is a centre that looks at the reuse of a number of materials, with the main aim being the reduction of materials ending up in landfill. So the shortage of landfill space has become a central issue for many countries, and traditional landfill closure often involves various layers of primary raw materials to form a barrier between the waste and its surroundings. And so closing a landfill also adds to the consumption of aggregates and therefore has a negative environmental, economic and social impact. And then at the same time, we see that there are lots of construction projects out there that result in a surplus of excavated soils, and then they are typically landfilled as well. So we're looking at finding a better use for all these different types of soils and how we can kind of create a better circular economy and reuse of different materials. So one of the materials we're looking at the moment, which carries on quite nicely from Sara's presentation, is how we can reuse lime cement stabilized clays. And in Norway, we have a lot of soft soils. We have soft clays and also quick clay. So we do use a lot of ground improvement in order to go on with our construction projects. And so, yeah, we're looking for ways to reuse this material rather than send it to landfill. So the aim is that we can use this material as a sealing layer for landfills. So to create a barrier that gives us a long-term performance and protection. And that may also allow for the reuse of the land once the landfill is completed. So firstly, we carried out a range of laboratory experiments on reconstituted samples, and we've also carried out full-scale compaction trials in the field to look at what compaction properties we can achieve. And the geotechnical testing revealed that the lime cement stabilized clay can be classified as an intermediate to very fine soil. And it has a fairly high plasticity as a silty clay. And we achieved quite good compaction in the field and also then reasonable hydraulic conductivity values. We do, however, see that for the lime cement stabilized clay, the results varies a little bit more than maybe for some other materials that we've tested. So it's still ongoing, but positive in terms of reuse. So we're now at a point where we're doing a pilot test, and the island that we can see in this picture here is actually a landfill for hazardous waste in Norway, and it's also where we do a lot of research. So we have a very close collaboration with NOAA, who owns this, and we've established pilot tests. Here's a picture from the establishment of that, and we're actually looking at different materials with the aim of finding like a sealing layer. So we're looking at dry crust clays, we're looking at press filter residues, and we're looking at this lime cement stabilized clay in 4 different test cells. And they're built up in this way so that on top we have a protection layer to prevent erosion and protect and effects of.
Is this a landfill?
Yes, Mark. Pardon?
Is this a landfill?
This island? Yes.
Yeah.
Yeah. So they receive a lot of industrial wastes in Norway, and it's got limited capacity, which is also a big motivation for us trying to reduce the amount actually going there. Pardon?
For the first time, I feel I don't mind living on a landfill.
No, exactly. It's actually it's quite nice. It's the landfill, but also it has some protected natural areas around it. So the public are allowed on the green areas around, and they can go walking and things like that. So
you're trying to save the island.
Yeah, but it's also, we don't want it to be an eyesore for the people who live close by. So they try to do a lot for the environment around. Oh, I don't know. I don't have any numbers on that.
Are we looking at half
Maybe
of it or 10% of it?
I think maybe we're looking about 75% of it.
Oh, okay.
So it's not huge, but it's an old quarry, and now we're using the sort of empty quarry to fill. Can you say that again, Mark, please? Yeah. But no, it's a beautiful place despite being a landfill for hazardous waste.
Nice.
Yeah.
Go.
Right. So we've got this protection layer on top of the materials we're testing because we need to protect it from the environment to prevent excess heating and also freezing. So we have cold winters in Norway, so we get just the other day it was down to minus 12 degrees Celsius, and so we try and avoid these freeze and thaw cycles, or at least the extremes in our sealing layer, and also drying and wetting. So we've got a protection layer on top, and then the red soil that we can see, that is our lime cement stabilized clay as a sealing layer. And we have instrumentation in all of these layers, so we can keep an eye on temperature effects and how it affects the water content and electrical conductivity as well. And underneath each cell, we have a lysimeter, which measures the water that might percolate through the sealing layer. And this is being led to the side to a tipping bucket, so we can measure the amounts. And it also allows us to collect the water and do chemical analysis on that water. So this was constructed, the pilots were set up in the autumn of last year. So at the moment we are keeping an eye on this, and we have all these this instrumentation and real-time data that we're keeping an eye on. And then the plan is for this pilot to run for several years. So there will be more updates on these materials in the future. The second thing I wanted to touch on was construction on peat and the understanding of the behavior of peat. So this map shows, the brown areas show where you find the most peat. So it's typically in the northern hemisphere. And so there's lots of peat in Canada and Russia and in northern Europe. And peat is quite a problematic type of soil. It's organic soils and very low strength and very high compressibility. So it leads to differential settlements and slides. And in Norway, approximately 9% of our land is covered by peatlands. And in the past 30 years, peatland reduction has released more than 10 million tons of CO2. And about 60% of this was caused by the construction industry. So it's a common understanding now that we should avoid construction in peatlands because it stores a lot of carbon in the ground, and it's also a natural habitat that we want to protect. But we do see that there are cases where construction is inevitable, especially for critical infrastructure. So sometimes for roads, water and sewage, energy, etc. So we do need to understand how we can also build on peat in a more sustainable way. So I wanted to show an example of a recent highways project in the north of Norway. It's the E6 in the north. And this picture on the left shows, the red line shows the stretch of the peatland that they wanted to get across, and it's about 500 meters. And on the right, you can see a picture which shows that there's actually a lot of surface water. It's a very wet area to try and build across. But the geotechnical design team here went to great lengths to document the feasibility of building on the peat and finding a construction method where we could stay on top of the peat rather than replacing it. The thickness of the peat across this area was up to 4 meters, and so it would be quite significant if we were to excavate all that soil and replace it. So the principles that you kind of choose from is shown below here. So traditionally you would do what's shown on the left, that you would replace the peat so you don't have to worry about it, and put in a high quality fill instead. But what we were aiming to do here was to build our road on top of the peat with then a surcharge fill on top. And the design of this was actually enabled by some previous work carried out by colleagues, where they had done quite a significant job creating a database on the characterization of Norwegian peats. So they collected a lot of data from different sites and from projects across the years. So they had up to sort of 500 samples that they with tests, so that they could put together tables for properties of index data, strength and deformation characteristics. And so our design team could use these values that were presented, use conservative values, and come up with an alternative design to present to the client without too much additional investment. So they could use this database as a very good starting point. So the construction method is fairly simple, but still hard to carry out, and it basically requires you to work in careful steps. Where the first step is to put, you need to use geomesh and geotextiles to stop things just disappearing into the peat, and then carefully build up layers.
I've seen this happen.
Yes.
And you need also to mention, you need special equipment with large tracts. So you have
so one of the things here, so the peat is also a very weak soil, and so bearing capacity is a major issue. And so when they first started this construction, they did actually have some issues and struggled, and they needed to use very small diggers and very small tractors and build out their layers very carefully to avoid bearing capacity failure. So of course it's also more time consuming to construct in this way, but it allows you to have an end result where you can actually leave the peat in place. We also used a georadar to monitor the thickness of each layer, as it did vary, or to make sure that the material hadn't just disappeared into the peat. So yeah, carefully building up the layers and then putting a surcharge fill on top.
Yeah, you have to add to your slide, required the use of small diggers and tractors with large tracts.
Yes, yeah.
Very wide, because I've used them in on thick, about 10-meter peats in Central Africa, in Nigeria, in the jungle.
Okay, yeah.
So I was looking hard for
geofoam, which doesn't exist there. So we had to.
Yeah.
So I'm very interested. Keep going to hear
Thank
what you
you.
did.
So what they did, we've then put a 2-meter extra fill on top to progress the settlements that we're expecting, because we're expecting about 2 meters of settlements as well in this material, and we don't want to build our road before most of the settlements finished. So this is then to be left in place, and when we have achieved the settlements that we've predicted, then you can remove your surcharge fill and establish your road. And the surcharge fill can also be reused within the project, so moved, further along the road, the line of the road. So here's just a picture showing part of the construction. So you can see sort of quite thin layers, and they're very carefully working their way across this very wet bit of land. And this is where we are at the moment. So right now we're watching the settlements. It's been about half a year since it was established, and we think we'll need a full year to see full settlements. And the longer the better. The longer we can leave the surcharge fill in place, the less settlements we'll see on the final road. So again, an ongoing project, but that is looking very positive.
Very, very nice. So the idea is to build a strong embankment that will settle evenly, or?
Yes. Yeah. So that's as well
you
the use of the georadar.
It doesn't really affect the settlement.
Yeah, so we've had an additional load, and then when we take that load away, the ground has been pre-consolidated to a higher load than it will be subjected to in the permanent phase. So there's still an element of creep. So the longer we can leave the surcharge fill, the better, yes. which luckily the contractor on the project has allowed for. So that's also a constraint. It's not always possible to build in this way if you have very strict timelines. But it's a good way to show that you can build more sustainably if you allow the time for it as well, because it's quite a simple method really. But in areas where if you have a very strict timeline for your project, then this wouldn't be an option in the same way.
The problem, I had once a contractor do this without stabilization, without the geotextile, and he would keep adding loads and backfilling. We come back the next day and the whole berm or embankment would settle and disappear. In the jungle, I'm telling the story for everyone and the audience. You could hear the trees cracking and falling 40 meters away.
Wow.
Yes, thank you. And you could see here 40 meters away, as the road is being constructed and the backfill elevated, it would sink. And of course, the proof that Terzaghi was right, there is a circle underground, and you could see 40 meters away, the trees falling. We thought that the Bushmen are attacking us. So, very interesting. And one of the options is to keep backfilling, but this is ruining the earth and very expensive until you go to your first option, which is removing peat or compressing it to the max.
Yeah.
And that's what they did, unfortunately. They kept borrowing material, laterite, which is like sand. But I like this option better.
Yeah. So if you fill without any geotextiles or anything, then you are essentially replacing the peat, right? You're just sort of forcing it away because it's so soft. So by doing this, we hope that we can preserve the peat and the carbon stored in the peat.
Yes.
Yeah.
If you could,
my last slide was just a quick summary
Yeah, just
the-
let me tell the audience and you
Okay.
about the settlement curves. Can you go back to that
Oh
slide?
yeah, sure. Yeah, so this is
Can you go back to this? Yes, this one.
yeah.
Yes.
Yeah, so this
So I
shows
want to tell you here, you're looking at 1.5 meter, 1.5 meter of settlement in less than a year.
yes.
Let's have a bet, all of us. How far will this settlement go? Because you see, it's slowing down the slope. So where would it touch the asymptotic? In 2 years, you think?
2 years, I think green one might reach, we have to be a little bit conservative, maybe 1.6. It's a linear graph on x-axis, so half a year, about 6 months. Long way to
Yeah.
And
go. The creep will
Dawn, are you
continue.
testing the embankment on different in the middle, on the
Yes,
sides?
we are. So so that's one thing to say about this slide, that the graphs, the curves starting from 0, they start measuring after the first 1.5 meter fill is put in place, because that's when you have the largest movement. So we're not counting those. There is an element of not just normal settlements, but you know, larger movements in the peat when you place that first fill. So that's this the curve starting from 0. They're measuring from 1.5 meter of fill, and the curve starting at 50, they are measuring from the top of the fill. So when the surcharge fill is in place, they're measuring on top of the embankment.
So just to make sure I understand right, you have telltales like tubes where you measure the lower part and then you measure from the top, which are the curves starting from 50, right?
Well, I think they're slightly different. So the lowest ones are settlement plates underneath the fill, and on top, I don't know. I think they're just measuring specific points. It's like settlement
So could
bolts
we
or
say
something.
that whatever deformation in between is the self-settlement of the fill you're putting?
Yeah. Well, there shouldn't be too much settlement within the fill.
Correct, because it's compact, right?
But when you start measuring on top of the fill, a lot of the settlement has happened already as you build it up, right? So that's why you see less settlement in the measurements starting from the top of the fill, because it does happen fairly
I want to
quickly.
tell you about settlement. If it's occurring in a uniform way, we don't worry too much. In Mexico City, for example, they deal with settlements up to 10 meters on buildings. So if you live on the first floor, at one point you will be living in a basement. This is a true joke, but it's not a joke, but they deal with that. So I'm not scared to see 1.6 meter settlement when the book tells you maximum of 2 centimeters is allowed in buildings and stuff. So if you know how to control it, don't worry, keep going.
Absolutely. Yes. So the fact that we've had this database on the behavior of peat and been able to understand the material, it means that we've predicted settlements. So it's not a surprise to us to see these settlements. You know, we know what to expect, and you can kind of follow the data and be confident that it matches what you see in real life, matches your design, and that we're on the right track. So yeah, we're expecting sort of around 2 meters of settlements, but it of course varies across the stretch, as well as the thickness of the peat varies and things like that. So, but we're keeping an eye on it, and maybe in a year's time we'll be ready to build a road on top. Okay, any more questions on that one?
Not me.
No. Okay, then I just it's just this quick summary slide to say that in both of the examples that I've shown, we show that alternative solutions and more sustainable solutions can reduce the amount of soil that we send to landfill, but it also reduces the need for using virgin materials and transporting materials into your project rather than using what is there. And we see that there is a need for understanding the long-term behavior of materials, just like I think we've all spoken about, when we're testing new materials and alternative binders and things like that, the durability aspect and what will happen in a much longer term becomes quite important. So we need more research into that. But there is a huge potential for more sustainable solutions when the industry and the project owners are willing to adopt our research and construct things in a different way. So yeah, that's
fantastic.
It for me.
Always follow research and theory, because if we don't and we just follow the code, we're going to stay here. In conclusion, just to make you smile, I'm going to share my screen. I'm thinking of
There we are.
so this is the picture was showing this area. So you were showing about 1/3 of the island, and there is a nice lake here. If you can find a piece of property for me there, I will move to Norway. And oh, did you see it's -3 degrees? So you were right. It's pretty cold up there.
Oh yeah, no, it's not too bad today. It's a
Thank you
beautiful
all.
sunny day, but very cold.
Wonderful. I hope it will stay sunny everywhere you go. Thank you. What you just did is very important, giving from your time and your know-how, and sharing with everyone around the world, especially the geotechnical engineers and the young geotechnical engineers looking up to us to change the world and make it better.